Bismillahirrahmanirrahim. Assalamu alaikum, students. Today we are going to discuss another important idea. So let me write the name of today's topic, that is application of statistical method to gases. Let me underline this and let me change the color. We will see in this topic we come across the idea of the density of states. So let us discuss this. In the last lectures, we applied the statistical method, remember, to an assembly of distinguishable localized particles. So now we know how to deal with such an assembly. So whenever we have assembly of particles which are distinguishable, or they are distinguishable due to their locality, then the statistical method we discussed works and we use that. But when we use this method to gases, we have to incorporate two new ideas into our method. Only then we can use the statistical method. So in case of gases, you cannot use the method we discussed directly, because there are two things which we have to address. First thing, let me write it in black. Let me write, we need two ideas. What are two ideas which we have to consider in the application of statistical method to gases? Let me discuss the first idea. Now, the first idea concerns the one particle states. So first idea concerns the one particle. Let me adjust my pen. One particle states. You know, one particle state means the states which the particles in the assembly can occupy. Now, what is the issue in case of gases with regard to the one particle states? Remember, A gas particle is confined to a large macroscopic box of volume V. Let me write it because it is important. A gas particle is confined to a large macroscopic box of volume V. Remember, volume in which particle is confined is affecting the particle states. That means the energy states which a particle can possess depends on the volume in which it is confined. Now, gas particle is confined to a large macroscopic box of volume V. That, in other words, means in a gas, the particle is free to move. So effectively, it is confined to a large macroscopic box of volume V, whereas a localized particle, which we have already discussed, is confined to an atomic cell of volume V by N. This is localized particle. So localized particle is confined to a small volume V by N, where V is the volume of the total sample and N is the number of particles in the sample. Since it is localized, it is available or confined in a small volume, or you can say small cell or atomic cell of volume V by N. So this is the first difference. Gas particle is free. It is confined to large macroscopic box of volume V, where the localized particle is confined to small volume V by N. Now what happens because of this? The energy levels of a gas particle are extremely close together. Let me write it on another page. Because of this reason, the energy levels that is means the single particle states of a gas particle, energy levels of a gas particle are extremely close together. With large numbers of them, which are astronomical numbers, being occupied at any reasonable temperature. I repeat, the energy levels of a gas particle are extremely close together, and large number of them, in fact astronomical numbers of them, are being occupied by the particles in the gas at any reasonable temperature. This is in marked contrast with the localized case, in which The energy levels are comparatively far apart, and the occupation of only a few need to be considered. So this is the first idea in case of gases, which is different than that of an assembly of distinguishable localized particles. What is the second thing or second idea which is different in case of gases? So let me discuss that. The second idea is how to deal with how to deal with the indic in this distinguishability of gas particles. Remember, gas particles are not distinguishable. They are indistinguishable. They are not localized, so we cannot use their localization because they are not localized to distinguish between gas particles. So they are fundamentally is indistinguishable. Now their indistinguishability is vital to the counting of microstates. When we have to count the microstates pertaining to an assembly of gas particles, we have to take that into consideration. So these are two ideas which we have to deal with. First is that gas particles are confined to large volume. Because of that, we have large number of energy levels pertaining to a gas particle. They are extremely close together, and large number of the energy levels are occupied at any reasonable temperature. Second thing is the gas particles are indistinguishable. Now, both these ideas are essentially quantum mechanical. Now, how we deal with these two things, let us discuss that. Remember, in quantum mechanics, we have discussed it, how we specify state in quantum mechanics. We have already discussed an example pertaining to that. So in quantum mechanics, how we deal with this issue, in quantum mechanics, the state of a gas particle is discussed in terms of the wave function. And the basic properties of such wave functions are dominated by pure geometry only. Consider, let me use screening. Consider a particle, a gas particle, in one of its possible states described by a wave function psi xyz. The time dependence of the wave function is not included because in thermal physics we only need the stationary states of the particle, right? Because we talk of thermal equilibrium, and in thermal equilibrium we are fixing the time. So we need only stationary states. So we are ignoring the time dependence of the wave function. So If we have a particle in one of its possible states, which is described by a wave function psi, what do we know about such states in which the particle, when particle is confined within an otherwise empty box of volume V? Let me repeat it. I told you that if we consider a particle in one of its possible states described by a wave function psi of x, y, z, now what we know about such states when the particle is confined within an otherwise empty box of volume V? For convenience, let us assume that the box is a cube. Box is a cube. Let me write it neatly. Box is a cube of side A. So the volume of the cube is then A cube. So if we assume that the particle is confined in this cube having volume V equal to A cube, where A is the side of the cube, and we further assume that the confined means that it must satisfy the boundary condition psi is equal to 0 over the surface of the box. So psi is 0 over the surface of the box. So we have a particle which is in one of its possible states. State is described by wave function psi, and we assume that the particle is in a box in the shape of a cube of side A, so its volume is A cube, and we assume that confined means that psi is equal to 0 over the surface of the box. Now the only way to achieve a possible wave function which has these characteristics which we discussed is to ensure that a precisely integral number of half waves fit into the box in all three principal directions. Remember, this problem is the three-dimensional analog of the one-dimensional standing wave normal modes of the vibrations of a string. So, to be specific, we choose the origin of coordinates at one corner of the box. So when we do that, we choose the origin of the coordinates at one corner of the box. The wave function is then given by a standing wave. Let me write. The wave function is given by a standing wave of the form psi is sine. I'm not writing equality. We're ignoring the constants. Sine of n1 pi x by a times sine of n2 pi y by a sine of n3 pi z by a. Let me name it first. So this is my equation first. So this is the wave function pertaining to this particle. Sine of n1 pi x by a times sine of n2 pi y by a sine n3 pi z by a. Where the positive integers, let me change the color of my pen, where the positive integers n1 comma n2 comma n3 which are equal to 1 2 3 so on, simply give the number of half waves fitting into the cubical box of side A in the respective directions. That means n1 is the number of half waves which fit in the cubical box along x direction. N2 is the number of half waves which fit into the cubical box along y direction. And N3 is the number of half waves which fit into the cubical box of side A along z direction. Right? So now the state is specified by these three numbers n1, n2, and n3. We've already discussed this in the example when we discussed the specification of state in the light of quantum mechanics. So earlier we used the notation of state specification by J. So specifying the state or labeling the state by J is equivalent to the specification of the states by three numbers n1, n2, n3. Now it is useful to write this equation 1 in terms of the components of a wave vector k. Let me write. Let me use another page for that. So it is useful, I should say, it is useful to write equation 1 in terms of the components of a wave vector k. Wave vector k as psi is of this form, sine of kxx, sine of kyy, sine of kzz. Let me name it equation second, where kx, ky, and kz are the components of the wave vector k, and they are equal to pi by a n1 pi by a n2 and pi by a n3. This is here. So kx is pi by a n1, ky is pi by a n2, and kz is pi by a n3. You can see when you write it this way, equation 2 is identical with equation 1. You're only expressing it in terms of the components of the wave vector k with the components kx, ky, kz as explained. Now the possible states for the wave, which are in fact the states of the gas particle represented by that wave function, these possible states for the wave are specified by giving the three integers n1, n2, and n3. That's by specifying particular point k in k space. So point k in k space represents or specifies the state. This is important. We talk of now a space called k space, mathematical space, and each point k in that k space specifies the states of the particle, right? This is a valuable geometrical idea. What it means is that all the possible k states can be represented on a single picture by a cubic array of points in the positive octant of k space, the spacing being pi by a. Remember, the kx, ky, kz are only positive. So when we talk of this k space which we are considering, in that k space, we have to consider only the positive octant. And in that positive octant, the points are uh, uh, specifying the state or representing the state of the particle, states of the particle, and those points have spacing of pi by a. Pi by a is the spacing of the points. Check it at home. Now important is, now since the spacing between the points and each point in k space in the positive octant of k space is a state, and spacing between the points is pi by a. A is the side of the cube under consideration, side of the cube, which is our volume in which particle is confined. Now, because of the macroscopic size of A is large, macroscopic size of A of the box, because of this spacing is very small in all realistic cases. So in the consideration of gases, what happens? The macroscopic size A of the box is macroscopic, is large, and the spacing is very small. Spacing between points or spacing between states is very small in all realistic cases. In most cases, the states are so numerous that our n particles are spread over very many more than n states. In fact, most occupation numbers are 0. Now, under these conditions, it is clear that we shall not wish to consider the states individually because they are large. That would be to specify the state of the assembly in far too much detail. Rather, we choose to group the states. This is important. We group the states. So what we do, I change the color. We group the states. And to specify only the mean properties of each group, so we group the states and we choose to specify only the mean properties of each group. And the use of case space gives an immediate way of doing this grouping, right? Or sometimes we call it graining of states. Let me give an example. Let us suppose so for example, let us suppose we wish to count the number of states the number of states in a group whose k vector lies with x component between kx and kx plus delta kx with y component between ay and ky plus, let me adjust my pen, ky plus delta ky and with z component between kz and kz plus delta kz. So we suppose we wish to count the number of states in a group whose k vector lies with x component between kx and kx plus delta kx, y component between ky and ky plus delta ky, and z component between kz and kz plus delta kz. We call this number of states in this specified range as, let me use another color, g of kx, ky, kz times delta kx, delta ky, delta kz. So this thing is representing this group. That means g of this function g, which is depends on the components of k vector, times this delta kx, delta ky, delta kz. Understand this delta kx, delta ky, delta kz is actually what? It is the volume in this case space which we are constraining, right? So it is the extension in space, in this case space, right? So this whole thing is representing what? Let me do it neatly. This whole thing, I should use another color here. This whole thing, this g of kx, ky, kz times delta kx, delta ky, delta kz is representing the number of states in a group whose k lies with x component between kx and kx plus delta kx, y component between ky and ky plus delta ky, and z component between kz and kz plus delta kz. Now, since the states are evenly spread in k space with the spacing pi by a, this number can be simply written as g of kx, ky, kz times delta kx, delta ky, delta, this is delta here, delta kz, this is equal to a by pi whole cube times delta kx, delta ky, delta kz. This is equation third. So I'm telling you that the number of states in a group whose k lies with x component between kx and kx plus delta kx, and y component between ky and ky plus delta ky, and z component between kz and kz plus delta kz, or you can say the number of states in this volume in k space in the positive octant which you are considering delta kx, delta ky, delta kz is given by this equation a by pi cube times delta kx, delta ky, delta kz. I will give you this as your home assignment. This is a simple exercise. Check it. So this is your one of the homeworks. Check this at home. Now this function g defined so is the density of states in K. This function G is, this function is representing here the density of states in K, which we talked about at the start of the lecture, this density of states. So this is density of states in K. Now its constant value simply sets out that the states are uniformly separated in K space. You can see its density of states here is simply A by pi whole cube. So this density of states is constant. So states are uniformly separated in K space. Now this is a significant and useful idea, because using this you can find number of states in any group. You can evaluate number of states in any group from the volume in the K space occupied by the group together with this equation 3. For example, to discuss the equilibrium properties of gases, we make extensive use of another density of states function. I need to write it because I think it is worth of writing. It is important to discuss the equilibrium properties of gases we make extensive use of another, let me change the color, it is another function, we make extensive use of another density of states. Let me clear it. Another density of states function, another density of states function, G of K, which relates to the scalar magnitude of K only. Scalar magnitude of K. Oh, let me get my pen back. Scalar magnitude of K only, irrespective of its direction. Set my pen. irrespective of irrespective of its direction, its definition is that, let me write it another color, g of k delta k is the number of k states with values of scalar k, that means its magnitude, only between, let me write it neatly, between k and k plus delta k. Now its form may be derived from equation 3 from an integration over angles. Now since the density of states in k is constant, I will write directly the answer. Let me write it. G of k delta k is a by pi cube times 4 pi k square delta k over 8, which can be written equal to v by 2 pi whole cube times 4 pi k square delta k. This here k square, let me write it a bit neatly. I name it equation 4. G of k delta k is equal to a by pi whole cube times 4 pi k square delta k by 8, which can be written as, we have replaced a cube by v because v is the volume of the box. So it is v by 2 pi cube, 8 in the denominator we replaced by 2 cube. So it is v by 2 pi cube times 4 pi k square delta k. Now you can derive it from equation 3 as I told you, which is previous equation. You have to make integration over angles. You will get this result. So this is your another homework. Let me write it here. Check this at home. Now in this equation 4, 4 pi k square delta k, that is this, let me, this 4 pi k square delta k arises as the volume of a spherical shell of radius k and thickness delta k. And the factor above of this 1 by 8 here, this factor 1 by 8, comes since we only require 1 by 8 of the shell for which kx, ky, and kz are all positive, that is the positive octant, right? Now this equation 4 is the most important result with regard to the statistical, with regard to the application of statistical method to gases. So I stop here. Before stopping, I will continue with this. It is not complete in the next lecture. So before stopping or leaving you, I will first summarize today's lecture. So our lecture was related to the application of statistical method to gases, and I told you when we apply statistical method to gases, it is different from the method we use it to assembly of distinguishable localized particles, and it involves the idea of density of states. Two things are here different, two new ideas we need to address. First thing is concerning the one particle states. A gas particle is confined to a large macroscopic box of volume V, while as for a localized particle, it is confined to a small volume atomic cell V by N. So due to this, the energy levels of a gas particle are extremely close together. Second thing, the gas particles are indistinguishable, and you have to take that into consideration because you have to count the microstates. Then we said these things are addressed by quantum mechanics. In quantum mechanics, the state of a gas particle is discussed in terms of a wave function. And what we do, we basically fit the waves in the box and find the wave function which is suitable or which has those properties. So we considered a particle in one of its possible states described by a wave function psi, and we considered it in a cube of side A with volume A cube, and we said by confinement we mean psi is 0 over the surface of the box. So the wave function which has these characteristics is of this form, where n1, n2, n3 are positive integers, 1, 2, 3, and so on. So state here is specified by these three numbers, n1, n2, n3. Then we wrote this equation 1 in terms of the components of a wave vector, k, with components kx, ky, kz, where kx is pi by a n1, ky is pi by a n2, and kz is pi by a n3. So we said the possible states for the wave are specified by giving three integers, n1, n2, n3, or that is by specifying a particular point k in k space. And we said that all the possible k states can be represented on a single picture by a cubic array of points and the positive octant of k space with spacing pi by a. Then we said because the macroscopic size A of the box because of its macroscopic size, the spacing between the states, that is the spacing between the points in the K space, is very small in all realistic cases. As I told you, in most gases, the states are so numerous that our n particles are spread over many more than n states. Then what we do under these conditions, we do not consider the states individually. Then what we do, we group the states and we specify only the mean properties of each group. And we use the idea of K-space for doing this grouping. Then I told you, if we have to consider the or count the number of states in the group whose k lies with x component between kx and kx plus delta kx, with y component between ky and ky plus delta ky, and z component between kz and kz plus delta kz. That number is represented by this product of the function g times the volume in K space delta kx, delta ky, delta kz. And this function g is the density of states function in K. And I told you that this is given by equation 3. This number of states in this extension delta kx, delta ky, delta kz is given by equation 3 equal to a by pi whole cube delta kx, delta ky, delta kz. And I gave you the home assignment to prove it or check it. Then I told you we talk of another type of density of states function when we talk of equilibrium properties of gases, right? That another function is simply g of k, where k is simply the magnitude of wave vector k. So we don't bother in this g of k about the direction of wave vector. So in this equation 3, this g is function of all the three components. That means per vector you have one function. That means if you it depends on the direction of k also. It doesn't only depend on the magnitude. But when we talk of this g of k, this is function of only the magnitude of the wave vector k. And this g of k delta k is number of k states with values of scalar k between k and k plus delta k. And I told you this can be derived, this expression 4 from equation 3, right? And I gave you this home assignment to check this at home. So I wrote this expression directly. G of k delta k is a by pi whole cube times 4 pi k square delta k by 8, which can be written as equal to v by 2 pi cube times 4 pi k square delta k. And I told you in this derivation of equation 4, 4 pi k square delta k is the volume of the spherical shell of radius k and thickness delta k, and 1 by 8 factor arises from the requirement of the requirement that we have to consider only positive octant in K space. So this is all for today. Go through all the video lectures. We will continue it in next lecture. Don't waste your time and do all the home assignments. So I leave you here. Assalamu alaikum. Thank you.